ஒரு animation, I wanted to show some animation also. இந்த சாப்டர் வந்து ஆக்சுவலி கொஞ்சம் விஷுவலைசேஷன் ஸ்கில்ஸ் கூட தேவைப்படுது. ஸோ ஐ வாண்டட் யூ டு விஷுவலைஸ்.
Sir,
ஸோ ஐ யூசிங் லைக் பேஸ்ட்
Your
மாடல் ஃபார் டுடே.
sir,
ஸோ யூ ஷுட் பி ஏபிள் டு see. நான் வந்து அதை ஷேர் பண்றேன்.
Manish, your voice is breaking. என்னன்னு
ஓகே
பாருங்க.
ஓகே, ஜஸ்ட் a minute. Okay, am I audible now?
Now it's okay.
Now
yes,
it's
sir.
audible? Okay, okay, fine. Yeah, good evening, children. So today I'm planning for the next chapter, that is system of particles and rotational motion. So we are looking at that chapter today. So இன்னைக்கு என்னன்னா, we will definitely look into formulas and stuff. But before that, I'm planning for an animation based teaching for today. So there is an animation which I've kept ready, a video. So we will look at the video, and then and there I'll explain, and then we will move on to problems at one go, so that it will be easy, because the visualization skills are more necessary. So that's the reason I've planned it, with an animation based lecture for today. Okay, so just let me know if you're able to see the tab that I'm sharing. I'll also share the audio. So I'll just put myself on mute and I'll just share it. எனக்கு சொல்லுங்க உங்களுக்கு அந்த இது வீடியோட அந்த ஆடியோ கேக்குதான்னு சொல்லுங்க. That's very important. Let me start sharing.
A rigid body is a system of particles with
Yeah, I hope it was audible, right?
Yeah.
Yes, sir.
Okay. Okay.
a finite size that do not get deformed under the influence of any external force. The distance between any two particles of an ideal rigid body does not change even when it is under the influence of external forces. Let us now observe a bicycle in motion. If A and B are two
So here they are talking about a rigid body. So rigid body is something that does not get deformed when external force is applied over it. Okay, நீங்க என்னதான் force apply பண்ணாலும் it's not going to change its shape nor its size. So both remains unchanged under the application of external force. Such bodies are called rigid bodies. So these are certain basic terms that you will have to know in this chapter. Okay, so we'll proceed.
are two particles on the frame. As the bicycle moves, the displacement is the same for both A and B. It implies that the velocity of particle A is equal to the velocity of particle B. This is also true with all other particles of the rigid body. Such a motion of a rigid body in which the velocity of all the constituent particles is the same at any instant of time is known as translational motion. Let us consider another rigid body, a door. Mark 2 points.
So now we learned about what is translational motion. So translational motion is basically where you consider two particles on a body, and when that body is moving, so the velocity at any instant of time has to be same for those given sets of points, because they travel equal displacement, or you say equal distances, in a given amount of time. Okay, so such particles undergo translational motion. So that's what we just now saw. We'll see the next part.
2 points P and Q on the door and observe their motions as the door is opened or closed. When the door is in motion, do the 2 points P and Q have the same displacement? Their displacements are not equal. Hence, the motion of the door is not translational. This is known as rotational motion of a rigid body. The door is fixed to a line passing through the hinges. This fixed line about which a rigid body rotates is called the axis of rotation. When a rigid body is in rotational motion, how do the different particles on it move? When a rigid body is in rotational motion, every point on it moves along a circular path with the center on the axis of rotation, and the plane of this circle perpendicular to the axis of rotation. The rotating blades of a fan, the steering wheel of a car, and the Earth's rotation are some examples of rigid bodies in pure rotational motion. In all these examples, the axis of rotation is fixed and the rigid body rotates about it.
So now we have seen what is rotational motion. So we have seen examples for rotational motion. So if you are going to choose any point, now then with respect to the motion of the body, it is going to execute a circle which is at a fixed distance from its center of axis, or the axis of rotation, as just they showed. Okay, so that is the basic idea. So now you guys have the idea between what is rotational motion and what is translational motion. So we have seen different examples. So I hope these two terms are clear to you, and as well as what is rigid body, that is also clear. Okay, so we have seen three concepts so far. So anybody has got any doubts, you can ask now itself. I hope it's clear what is rigid body, what is translational, and what is rotational motion. Shall we proceed further?
Yes, sir.
Yes. Okay.
Now, what is spinning top? How does the motion of the top differ from that of the rotating bodies shown earlier? Here, the top is rotating about an axis. This axis of rotation of the top is not fixed, but rotates about a vertical line passing through its point of contact with the ground. This rotating axis forms an inverted cone, and this type of motion is known as precession. Even the motion of a grinding stone is of this nature. The axis of the grinding stone rotates about a vertical line that is normal to the base of the lower part of the grinding stone. In these examples, even though the axis of rotation is not fixed, the point of contact of the body with the ground is fixed. Observe the motion of the rolling wheel of a bicycle. The motion of any rolling body is a combination of rotational and translational motions. If a rigid body is fixed to an axis or a point, its motion is pure rotational motion. If the rigid body is free, it can have pure translational motion, or a combination of translational and rotational motion.
Let us consider a system of n particles with masses m1, m2, mi, mn, and the positions of these particles represented by x1, y1, z1, x2, y2, z2, xi, yi, zi, xn, yn, zn. The center of mass of a given system of n particles is a point in space. If the center of mass C is represented by the coordinates x, y, and z, then x is equal to sigma mi xi by sigma mi, which is equal to sigma mi xi by m. Equation 1.
Okay. So we have seen different, types of motion. So now we are moving on to the next part, which is called center of mass. Okay. So center of mass, what do you understand by the term center of mass? As the term itself suggests that it is a center, center at which the entire mass of the object is said to be concentrated. So that's the basic idea. So when you take any object, there is a center of mass for that object. Okay, where the entire mass of that object would be concentrated. Okay, so that is the basic definition for center of mass. So here, with respect to the xy plane, or in two dimensions, we are trying to find out center of mass. Or if you're going to take three dimensions, including z-axis, then another variable also we are going to represent. Okay, so the basic formula for center of mass is we are multiplying the mass of the object or any particular particle along with its distance from that particular axis. If you say with respect to x-axis, the distance would be along x-axis, either positively or negatively. Okay, or if it's going to be y, again, positive y also is possible, negative y is also possible. So here they have represented using sigma. Sigma is nothing but a summation operator, which gives you the sum of all the particles along with their distances from the origin. So origin is our reference point. So sum of all the distances, you multiply the distance with the mass of the object at that particular point. Okay, upon the total mass of all the particles contributing in that particular object. So this is basically the formula for center of mass. We'll see this. This is quite simple. So we'll proceed.
Y is equal to sigma mi yi by sigma mi, which is equal to sigma mi yi by m. Equation 2. Z is equal to sigma mi zi by sigma mi, which is equal to sigma mi zi by m. Let this be equation 3, where m is equal to sigma mi is the total mass of the system. The location of the center of a mass of a system of particles depends on the locations of constituent particles and their masses. For example, consider two identical particles, each of mass 2 kg, located at points P of 2, 0, 0 and Q of 8, 0, 0. Since both particles are along the x-axis, even their center of mass lies on the x-axis. X is equal to sigma mixi by m, equal to m1 x1 plus m2 x2 by m1 plus m2, which is equal to 2 into 2 plus 2 into 8 by 2 plus 2, equal to 5. The location of the center of mass is C1, 5, 0, 0. Note that when masses of both particles are equal, x is a simple average of x1 and x2. What happens to the center of mass if the mass of the second particle is increased to 6 kg? x2 is equal to m.
Yeah. So I would like one of you to please try this out. When both the objects or particles had the same mass, they said it would be the center of mass would just be the average, right? That is in between. So now if it's going to be changed to 8 kilograms, then what would be the center of mass? Can you just calculate and tell me what would be the coordinate of center of mass? Just you apply the formula sigma mixi upon m. It's a simple calculation. I want you guys to try it and tell me what answer you're getting. Just give you a minute to try it. Quite simple. Yeah, where is the center of mass now? Have you calculated? You can use the same formula as before. Sigma mi(xi) upon m, which is, where m is the total mass. This time it is going to be 2 plus 6, which is 8 kilograms. Okay, I'll give you options. Option A is 4, option B 5, option C 6, and option D 8.
6, sir.
What is the answer?
6, sir.
Yes, 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 that's correct. Okay, good.
m1 x1 plus m2 x2 by m1 plus m2, which is equal to 2 into 2 plus 6 into 8 by 2 plus 6, equal to 6.5. The center of mass C2, 6.5, 0, 0, moves closer to the heavier mass.
Were you getting 6.5?
Yes, sir.
Yes, sir.
Okay, fine, fine, fine. Okay.
If we place one more particle of mass 4 kg at point R 6.5, 6, 0, where will the center of mass of the three-particle system be positioned? The given set of particles are on the xy plane.
Yes, try this out. This time it's going to be a three particle system. So where you have another object also which is placed and the coordinates are 6.5, 6, 0. Okay. So you need to work it out on a paper because your mind calculations might not be that accurate. Just work it out and tell me what answer you're getting. I'll just give you a minute to think. Yes, anybody with the answers? At least the first coordinate of center of mass. What is the x coordinate of center of mass for this case? 2 times 2 plus 6 times 8 plus 6.5 times 4 upon 12. How much is that giving you? You should have done by now. What's the first coordinate of center of mass? Anybody? The x coordinate? Y is y is even more easier. Okay, I'll give you options now. Okay, because anyways, because competitive exams you have options, but I want you guys to try it. Anybody's got the answer? You can tell me. It's okay even if you go wrong. No worries. We are here to learn. Yeah. What's the first coordinate? Anybody? Are you getting 5, 6, 6.5, 8.5? No idea. Yeah. Somebody wanted to tell something. You try to unmute. What's the first value? So I'm giving the options in the chat box. Just tell me which option is right. So which of the options are right? I've given you 4 options in the chat box.
B, sir.
Second one or the fourth one?
Option B, second one.
Second one, yeah. The second one is right. 6.5, comma 2 and 0. That's correct.
And hence the center of mass also lies on the xy plane. On simplification as shown, we get x is equal to 6.5 and y is equal to 2. The position of the center of mass is C3, 6.5, comma 2, comma 0. On observing the above cases, we can regard the center of mass of a system of particles as the mass-weighted average location of the constituent particles. In vector notation, the position of the center of mass of a given system of particles is given by R is equal to sigma mi Ri by m, where Ri is equal to xi into I plus yi into j plus zi into k is the position vector of the ith particle, and
Sir,
r is equal to xi
Yes.
um, yes, sir. I'll just jot it down if you don't mind. Just can you just
Yeah,
keep?
yeah.
Thank you.
You want me to pause this video here?
Yes, sir. I'm just writing it down.
Okay, okay. Just let me know when you're done.
Yes, sir. 1 second. Yes, sir. I'm done.
Oh, no.
plus yj plus zk is the position vector of the center of mass. If we take the center of mass as the origin of our frame of reference, then sigma mi into ri is equal to 0. Here, the sum is a vector addition. This equation can be split into three equations. Sigma mi xi into I is equal to 0. Sigma mi yi into j is equal to 0. And sigma mi zi into k is equal to 0. In the two-particle example discussed earlier, with masses 2 kg and 6 kg, if the center of mass is chosen as origin, then x1 is equal to minus 4.5 and x2 is equal to 1.5. Sigma mi xi into I is equal to m1 into minus x1 plus m2 into x2, which is equal to 2 into minus 4.5 plus 6 into 1.5, which is equal to 0. When we deal with rigid bodies of continuous distribution of matter, we need to replace the summation symbol sigma in equations 1, 2, and 3 with an integral symbol. The coordinates of the center of mass of a continuous mass distribution is denoted by x is equal to 1 by m integral of x dm. Y is equal to 1 by m integral of y dm. Z is equal to 1 by m integral of z dm, where m is the total mass of the body. The equivalent expression in vector notation is r is equal to 1 by m integral of r dm. We can make use of symmetry considerations while finding the center of mass of homogeneous and regular shaped bodies.
So now we have learned the subtle concept of center of mass and how to locate center of mass when distribution of particles are known to us in two-dimensional system and as well as three-dimensional system. Okay, and we have also learned the vector notation of center of mass. And if the center of mass, is being taken as the origin, then you understand that it's going to be totally zero because you know sigma mixi term itself becomes zero, and zero over something is obviously zero. Okay, because at that point, if the origin is going to be placed, or if you assume the origin is going to be there, then then it's going to cancel out. Okay, the left side mass and its relative distance cancels out with the right side mass and its relative distance, because we take into consideration the sign convention. Okay, now we are looking at regular shaped objects. Now, if you see objects which shapes are quite regular, the first object you can see here is a square. So you know that opposite sides are equal and parallel, and diagonals are also equal, and they bisect each other. So obviously, the point of concurrency of the diagonals of a square would be the center of mass for a square. The second one, you what you see is basically a hexagon. So it's a regular hexagon. So a regular hexagon is made of equilateral triangles which are joined together. You have six equilateral triangles joined together to form a regular hexagon, and you can see the point of concurrency of all these equilateral triangles gives you the center of mass of the hexagon. Same way you can keep moving, onto different figures. So their lines of symmetry, okay, or point of concurrency of diagonals is going to give you the center of mass. So we'll see further.
For example, let us consider a homogeneous ring of radius r on an xy plane. Let us position the origin at the geometric center of the ring. If we consider a small element of mass dm in one direction, because of reflection symmetry, there is an identical element of mass dm in the opposite direction. If the coordinates of the first element are x, y, then the coordinates of the other element will be minus x, minus y. When all these elements are added, we get integral of x dm is equal to 0 and integral of y dm is equal to 0. This happens only if the center of mass of the ring coincides with its geometric center. Based on similar symmetry considerations, we can prove that the center of mass of a thin rod, uniform disk, uniform sphere, and other such regular bodies lies at their geometric center. Let us consider a system of n particles, with its total mass constant with respect to time. Now, consider particle I from the system. In the graph, its position is marked by vector Ri, and the center of mass of the given system of particles is denoted as R. Then, R is equal to sigma miri by m. Mr is equal to sigma miri, which is equal to m1 r1 plus m2 r2 plus m3 r3 and so on, plus mn rn. On differentiating both sides of the expression with respect to time, we get mdr by dt is equal to m1 into dr1 by dt plus m2 into dr2 by dt plus m3.
So here we are considering, a particle system. So when you're trying to consider n number of particles, okay, instead of three, if you're considering n particles, so in that case, so we are trying to differentiate on both sides with respect to time. So what happens when you differentiate? So it's nothing but, you call it it is the rate of change of it becomes the rate of change. Why do I call it rate of change? Because it's with respect to time. Okay. So when you can see that there is rate of change involved, so what happens to that particular quantity? What do you call it? Change in position with respect to time. Yes. What is that quantity called as? This is something that you guys are already aware of. So change in position with time is what physical quantity, basically. Is it speed or is it acceleration or is it velocity? What is it?
Velocity, sir.
Exactly, it's velocity. So we are trying to bring in velocity term here. That's the reason we are going for differentiating in the first place, because those objects are moving. So whenever an object is going to move, obviously there is change in position of the object. Even before moving, it would have been at one place, and once it's moved, it's going to change its position to another place, right? So velocity is definitely there. Okay, so that's basically what we are observing here in this particular animation. All right, let's proceed.
Into dr3 by dt, and so on, plus mn into drn by dt. mv is equal to m1 v1 plus m2 v2 plus m3 v3, and so on, plus mn vn, which is equal to sigma mi vi. Let this be equation 1, where v is the velocity of the center of mass and vi represents the velocity of the ith particle. Let us discuss with an example. Consider a body A of mass 0.3 kilogram is dropped from a certain height. At the same time, another body of mass 0.1 kilogram is thrown up vertically from the ground with an initial velocity of 10 meters per second. Find the initial velocity of the center of mass of the system of these particles. For the body A,
So I'm pausing it here for you guys to try. You just try this and tell me what answer you're getting. Yes, anybody got the answer? You have mass here, right? And they're asking you the initial velocity is given, they're asking you final velocity. Just you need to use the equations of motion, try to relate them for both and find out the final, the initial velocity of the system of particles for both. Okay, we'll see that.
If mass of the body is ma, and for the body B, if mass of the body is mb, then ma is equal to 0.3 kilogram and mb is equal to 0.1 kilogram. For the body A, initial velocity Va is equal to 0. And for the body B, initial velocity Vb is equal to 10 meter per second. Mass of the system of two particles m is equal to ma plus mb. That is 0.3 plus 0.1 is equal to 0.4 kilogram. If the initial velocity of the center of the mass of this two-body system is Vcm, then m into Vcm is equal to MAVA plus MBVB, or Vcm is equal to MAVA plus MBVB by m, which is equal to 0.3 into 0 plus 0.1 into 10 whole divided by 0.4 equal to 2.5 meter per second. On differentiating equation 1 with respect to time, m dv by dt is equal to m1 into dv1 by dt plus m2 into dv2 by dt plus m3 into dv3 by dt and so on, plus mn into dvn by dt.
So you see here when you differentiate it again, so the rate of change of velocity with time. Okay, so that is basically the term that we are looking at. So what is the rate of change of velocity? Which quantity that does that indicate?
Acceleration.
That's correct. It indicates acceleration. So you can also relate acceleration here. And what is mass times acceleration as per Newton's second law? M into A.
Force, sir.
That's correct. You get force. Okay. So you can also relate force here. They're bringing in the relations. That's how the system of, when you have system of particles in motion, so you can see that they are related to, they have obviously force. So there is an external force that's causing them to move. Okay, so we'll proceed.
ma is equal to m1 a1 plus m2 a2 plus m3 a3 and so on, plus mn an, which is equal to sigma of mi ai. Let this be equation 2, where a is the acceleration of the center of mass and ai represents the acceleration of the ith particle. Now, let us find the acceleration of the center of mass of the system of two bodies discussed in the earlier example. We will also describe the motion of the center of mass. Solution. If the downward direction is taken as positive and the acceleration of the center of mass is taken as a, then acceleration of A is equal to acceleration of B, which is equal to g. That means A of A is equal to A of B, which is equal to g. And M into A is equal to MA AA plus MB AB. Therefore, A is equal to 0.3 into G plus 0.1 into G whole divided by 0.4, which is equal to G. That means the center of mass of the system of two bodies will have downward acceleration g. Since the center of mass has initial velocity in the upward direction and acceleration in the downward direction, it initially moves up with decreasing velocity and reaches a maximum height and then start moving down. But MIAI is equal to Fi, equal to the net force acting on the ith particle. MA is equal to F1 plus F2 plus F3 and so on plus Fn, which is equal to sigma Fi. The net force on a particle may be an external force or an internal force. Fi is equal to Fi internal plus Fi external. The internal forces are exerted by one particle on another and forms action-reaction forces. F12 is equal to minus F21. The vector addition of all these internal forces acting on all particles adds to 0. Sigma Fi internal is equal to 0. Hence, MA is equal to sigma MIAI is equal to sigma Fi external and is also equal to F external. Let this be equation 3. So, the acceleration of the center of mass A is equal to F external by M. What is the physical meaning of this equation? MA is equal to sigma MIAI.
So for center of mass of system of particles which are in motion, relative motion with respect to their positions. So then they have proved Newton's second law using the formula of center of mass. So wherein force is equal to mass into acceleration. So the same thing they are asking here as a question. So the physical meaning of the equation is obviously from Newton's law. So you can see that provided mass is not changing, the positions are changing with respect to time. So in that case, so is there an external force? That is what is the question. Okay, so this is quite simple. So we'll move on.
Is equal to sigma Fi external of a system of particles is independent of the internal forces acting on it. 3. These conclusions are true for any system, a rigid body or a group of particles. When a spinner bowls, the ball may have a complicated rotational and translational motion, but the center of mass of the ball will have only translational motion. A gymnast performing an event on a pole will have a complicated motion, but his center of mass moves along a parabolic path. What about the linear momentum of the system of particles? We know that mv is equal to m1 v1 plus m2 v2 plus m3 v3 and so on, plus mn vn, which is equal to sigma MIVI, as Pi is equal to MIVI. MV is equal to P1 plus P2 plus P3 and so on, plus Pn, which is equal to sigma Pi. But for a system of n particles, the linear momentum P of the system of particles is P is equal to P1 plus P2 plus P3 and so on, plus Pn, which is equal to sigma Pi. Hence, P is equal to mv. Let this be equation 4. The total momentum of the system of particles is equal to the product of the total mass of the system and the velocity of the center of mass. P is identical to the linear momentum of the center of mass of the system of particles. On differentiating equation 4 with respect to time, dP by dt is equal to mdv by dt, which is equal to ma equal to F external. F external is equal to dP by dt. This is Newton's second law of motion applicable to the system of particles. If the external force acting on the system of particles is 0, then F external is equal to 0. dP by dt is equal to 0, and P is constant. This is the law of conservation of momentum applicable to a system of particles, which states that if the total external force acting on a system of particles is 0, then the linear momentum of the system is constant. A rigid body may have both translational and rotational motion. In such cases, it is usually convenient to work with the reference frame that is attached to the center of mass of the system of particles. The motion of a rolling wheel can be considered as translational motion of the center of mass and rotational motion of all other particles about an axis passing through the center of mass. As the moon revolves around the Earth will also have the motion as shown to keep their center of mass fixed. When the motion of this system is influenced by the sun's attraction, the center of mass of this system will have pure translational motion.
If the product of two vectors A and B
So we have looked about different aspects of a system of particles until now. So we have seen how the total momentum is also conserved and under what circumstances when external force is going to be 0. So we can see that when there is no constant force acting on the object, what's going to happen to the system of particles. The same way we have also learned about different types of motions so far. So the basic idea is, I hope it's clear. So now we are moving on to the vector notation. So vectors already, I think we have come across the concept of vectors, but still let's look at it, the basic concept, so that it will be a quick recap. Okay, so we have different types of vector product. We have dot product of vectors. We have cross product of vectors. Okay, so the basic aspects is what we are going to see. Okay, so we'll see that.
is a vector C, then C is called the vector product or cross product of A and B and is read as A cross B. The magnitude of the vector product C is equal to the product of the magnitudes of vectors A and B. and the sine of the angle, theta, between them. When the value of theta changes from 0 to pi by 2, the value of sine theta changes from 0 to 1. And hence, the magnitude of a cross product changes from 0 to AB. What is the direction of vector product C? The direction of vector product C is perpendicular to that of vectors A and B. In other words, vector product C is perpendicular to the plane containing vectors A and B. There are two simple rules to determine the direction of a vector product, namely the right-handed screw rule and the right-hand rule. When a right-handed screw is placed perpendicular to the AB plane with its head on it and rotated from A to B through the smaller angle, then the motion of the screw indicates the direction of the vector product of A and B, that is, C. The other rule is the right-hand rule. Stretch the right-hand palm as shown and place a long vector A perpendicular to the AB plane. If the fingers can curl from A to B through the smaller angle, then the direction of the thumb indicates the direction of the vector product of A and B. Now let us study some properties of vector products. The vector product of two vectors is not commutative. That is, A cross B is not equal to B cross A. Although the magnitudes of A cross B and B cross A are equal. They are opposite in direction. However, A cross B is equal to minus of B cross A. Vector product is distributive with respect to vector addition. Consider three vector A, B, and C as shown. Let's construct vector B plus C. And draw the vector product A
675 प्लस नंबर लाकर डॉक्टर बनना है, ये सबसे बड़ा सपना है.
cross B plus C. Next, let's draw the vector product A cross B and A cross C. Then draw a vector A cross B plus A cross C. This vector coincides with the vector A cross B plus C. Hence, the vector product is distributive with respect to addition. The vector product does not change its sign under reflection. That is, if we replace A with minus A and B with minus B, there will be no change in the sign of A cross B. What is the vector product of two identical vectors, say A and A? It is equal to 0, because for theta is equal to 0, sin theta is equal to 0. If we consider unit vectors I, j, and k along the three given axes, then I cross I is equal to 0. Similarly, j cross j and k cross k are also equal to 0. The vector product of I and j is equal to the product of the magnitudes of I and j. and the sine of the angle between them, which is 90 degrees. The magnitude of I cross j is equal to 1, since sine 90 is 1. The direction of the vector product I cross j is along the positive z-axis. Therefore, I cross j is equal to k. Similarly, we can prove the relationship between other unit vectors and their vector products. That is, j cross k is equal to I. K cross I is equal to j. J cross I is equal to minus k. K cross j is equal to minus I. And I cross k is equal to minus j. If the two given vectors, A and B, are expressed in terms of unit vectors I, j and k as shown, then the vector product of A and B is A cross B is equal to AXI plus AYJ plus AZK whole multiplied by BXI plus BYJ plus BZK. Upon solving and simplifying, we get A cross B is equal to AYBZ minus AZBY whole multiplied by I plus AZBX minus AXBZ whole multiplied by J plus AXBY minus AYBX whole multiplied by K. In determinant form, a vector product can be represented as shown.
Consider a rigid body in pure rotational motion about a fixed axis.
So now we have learned how to evaluate, the vector cross product by the matrix method. So by using a matrix method, that is a determinant rule, you can easily find out the vector cross product. Okay, so that's very simple. So by just calculating, doing a cross multiplication with appropriate signs, you can easily evaluate the cross product of any two given vectors. Okay, so that's an easier method. So that is what we typically approach for evaluating the vector cross products. Okay, so this chapter is quite simple. So but you need the visualization. That's the reason we are moving on with the animation. Okay, so we'll proceed further.
Axis. As you have already studied, each particle of the rotating rigid body executes uniform circular motion. The center of the circular path is on the axis of rotation, and the plane of the circle is perpendicular to the axis of rotation. Observe a particle at P in the rigid body, that is, at a perpendicular distance r from the axis of rotation. Let O be the center of the circular path of the point. While the rigid body is in rotational motion, if the position of the particle is changed from P to Q during a small interval of time, delta t, then the angle POQ is called the angular displacement. In the SI system of units, angular displacement is measured in radian. In fact, when the rigid body is in pure rotational motion, the angular displacement of any of its particles is the same and is equal to the angle through which the rigid body is rotated about the axis of rotation. if the angular displacement of a rigid body is delta theta during a small time interval of delta t, then the average angular velocity of the particle is defined as the ratio of delta theta to delta t. The limit of this ratio as delta t tends to 0 is called instantaneous angular velocity and is represented by omega. Angular velocity omega is defined as the rate of angular displacement and is measured in radians per second. Note that the angular velocity is a vector quantity. If the right hand's fingers are curled in the direction of the rotation of the body, the direction of the stretched thumb is the direction of the angular velocity omega. When a rigid body is in pure rotational motion, the angular velocity of each part of the whole body If the angular velocity of a rigid body changes with time, it is said to be moving with angular acceleration. The rate of change of angular velocity is defined as angular acceleration, alpha. Alpha is equal to d omega by dt. In the SI system, it is measured in radians per second squared. This is also a vector quantity and its direction is along the vector d omega, which represents the change in angular velocity. Now, let us consider an example. When switched on, a fan attains its maximum angular speed of 30 radians per second in 12 seconds. When switched off, it takes 120 seconds to come to rest. What is the angular acceleration of the fan in both cases? In the case of increasing angular velocity, we get the angular acceleration alpha 1 is equal to 2.5 radians per second squared. In this case, both angular velocity and angular acceleration are in the same direction. In the case of decreasing angular velocity, alpha 2 is equal to minus 0.25 radians per second squared. Here, the direction of angular acceleration is opposite to that of the direction of angular velocity. For a better understanding, let us compare the terms related to translational motion and rotational motion. Observe a rigid body rotating about a fixed axis with an angular speed omega. Let v be the linear speed of a particle p, that is, at a perpendicular distance r from the axis of rotation. When the rigid body is in rotational motion, if the length of the arc traversed by the particle in a small interval of time is s, then s is equal to theta into r. On differentiating with time, ds by dt is equal to d theta by dt into r. V is equal to omega into r. This is a useful relationship between linear and angular speeds of a body. In vector notation, we can represent the relationship between linear velocity v and angular velocity omega as v is equal to omega cross r. This is applicable to a rigid body rotating about a fixed axis, as well as to a rigid body rotating about a fixed point.
What makes a body rotate? For example, what makes a door rotate? Yes, a force is required to rotate a door. Will any type of force be able to rotate the door? If the force acting on the door is parallel to the axis of rotation, it will not be able to rotate the door. There will be no rotation if the line of action of the force intersects the axis of rotation. Now, consider a wrench used to loosen a bolt. Compare the turning effect of the force when it is applied at different points from the point of rotation. The turning effect of the force is more when it is applied at a farther distance. Compare the turning effect of the force when it is applied at different angles. The turning effect is maximum if the force applied is perpendicular. The turning effect of a force is called torque or moment of force. As seen earlier, torque depends on the applied force, where it is applied, and how it is applied. Now let us define the torque of a force.
So here we are discussing, the moment of forces. So based on how the force is being applied, you can see that the magnitude of the torque is going to vary. For instance, you have here a wrench, okay, that is, used to tighten a bolt, or you can use it to, untighten a bolt. So based on how the force has been applied, you can do the, you can perform the work of, locking or unlocking. Now that force is maximum only when it is, perpendicular. So how come only when it's perpendicular? Again, you get the information. You can consider, force as one vector and the other force as the displacement vector from the point or the axis of rotation. And the angle theta is between both of them. When theta is 90, you know that sine 90 is going to be 1, and hence the force would be maximum. And that's the reason, the turning effect is, much observed, or the magnitude of the turning effect would be greater when theta is 90. Okay, so that's the logic. So let's proceed.
Force. If a force F is acting on a particle located at R, then the torque acting on the particle about the origin is a vector defined as R cross F and is denoted by the Greek alphabet tau. Now let us try to understand what torque is. Torque is a vector and its magnitude is expressed as tau is equal to Rf sine theta, where theta is the angle between R and F. The direction of tau is perpendicular to the plane containing R and F and can be found using a right-hand rule. If either the direction of R or the direction of F is reversed, the direction of tau is reversed. If the direction of both R and F is reversed, there will be no change in the direction of tau. The magnitude of torque can be written as tau is equal to R into F sine theta, which is equal to R into F perpendicular, or tau is equal to R sine theta into F, which is equal to r perpendicular F. R perpendicular is called the lever arm or moment arm. Note that the torque defined here is about a specific point, usually called origin. The torque of the same force about a different origin is different. Hence, identifying the origin is very important. Torque can be zero if the magnitude of the force is zero, or if the line of action of the force passes through the origin. The SI unit of torque is Newton meter. Note that the dimensions of torque and work are the same. The dimensional formula for torque is ml square T minus 2. Even though the torque and work have the same dimensional formula, work is a scalar, whereas torque is a vector. Now, let us study angular momentum. If r represents the position vector of a particle of mass m and linear momentum p, then the angular momentum of the particle about the origin is defined as the cross product of r and p. The magnitude of angular momentum of the particle L is equal to rp sine theta, which can also be written as is equal to rp perpendicular or r perpendicular p. L is 0 when r is equal to 0, or when p is equal to 0, or when theta is equal to 0. The SI unit of angular momentum is kilogram meter square per second. We can find a useful relationship between torque and angular momentum. We have L is equal to R cross P. On differentiating both sides with time, dL by dt is equal to d by dt of R cross P, which is equal to dr by dt cross P plus r cross dp by dt. On simplification, tau is equal to dl by dt. The rate of change of angular momentum of a particle with time is equal to the torque on the particle. Now, we can extend the concepts for a system of n particles. The angular momentum of a system of particles about the origin is equal to the vector sum of angular momenta of individual particles taken about the same origin. This implies that L is equal to sigma Li, which is equal to sigma Ri cross Pi. On differentiating both sides of the expression with time and simplifying, we get dl by dt is equal to sigma tau I, where tau I is the torque on the ith particle of the system of particles. This is expressed as the cross product of Ri and Fi, where Ri is the position vector of the ith particle and Fi is the force on it. The net force on the ith particle may be external or internal forces exerted by other particles of the system. Thus, we categorize the total torque on the ith particle as the sum of torques due to external forces tau I external and torques due to internal forces tau I internal. As per Newton's third law, the forces between any two particles are equal in magnitude and opposite in direction and act along the line joining them. Due to this,
All right. So we have seen, we have looked at angular momentum. We have looked at what is torque. So let's just have a brief, recap about what we have seen so far. So we have looked at angular velocity too. So what's angular velocity? In simple terms, you can say that it is the rate of change of angular displacement with time. Okay. So which is also represented as delta theta upon dt. So d theta upon dt. So you can put it that way. And the units and the SI units for that is radians per second because it's angular velocity. There is a change in angle with time and hence it is radians per second. So that's the basic idea. And the relation between linear and angular velocity, not to mention, that's also quite important. So where you have v is equal to r omega, where v is linear velocity and omega is angular velocity. Okay, and r is nothing but the position vector of that particular particle from the fixed axis of rotation. All right. So these are certain things that you guys should be knowing. Same way, what is angular acceleration? Again, we can put it in simple terms as the rate of change of angular velocity. All right. And the unit for this is very simple because you know that acceleration has got the unit meters per second square, but angular acceleration would have got the unit radians per second square because it's at an angle. It's happening at an angle, and therefore you do the appropriate changes. All right. So that's one more. And then we looked at what is torque. Okay. So torque is nothing but the turning effect of force as we saw in the animation. So if a force is going to be acting on an object, so the tendency to rotate the object by applying appropriate force at the right place and at the right angle would give you a greater effect of turning. So that is your torque. In vector form, tau is equal to r cross f, where r is your position vector from the axis of rotation and f is nothing but your force vector. So when you expand the cross product, you get rf sine theta. So tau is equal to rf sine theta is the relation, the formula for torque. And the unit for it is Newton meters because force has got the unit Newton and the position vector r has got the unit meter. Combining both, you get Newton meter. And then we looked at angular momentum. So angular momentum is basically the moment of the linear momentum of the particle about an axis. That gives you angular momentum. So you can simply say that it's the product of position vector, cross product of position vector, and the momentum vector p. Okay, so when you again expand the cross product of between r and p, you get rp sine theta. And for this, the standard units is kilograms meter square upon second. Okay, that's the unit. So these are all the basic ideas that we have seen so far. Okay, and we have looked at the concepts pertaining to these, the animation videos. I hope they were quite useful because you are able to visualize it real time. Okay, so we have learned the basics. Just a few more concepts. We just have 2 to 3 concepts, left. We'll do that in the next session, and we'll wind up with this, and then start doing, problems. We'll see problems in the next lecture, competitive questions, and then we will proceed further. All right. Yeah. So that's it for today.
Thank you, Manish.
So we can proceed. Yeah. Yes, uncle. Welcome. Bye, children. Take care.
Thank you, sir.